Hey everyone, in this video we're going to talk about polynomial long division. So recall regular long division with numbers. I'll go ahead and display a few examples, and if you need to pause the video to refresh how this process works, please do so. But we can divide numbers like 16 into 79, 5 into 40, and 13 into 1234 by using long division, and we pick up what are called quotients and remainders. Putting it formally, for integers a and b, where a is the larger of the two, there are positive integers q and r, where r is between 0 and b, so that a can be written as b times q plus r. And whenever we do long division, we can find all of these new numbers, q and r. In this case, a would be called the dividend, b is the divisor, q is the quotient, r is the remainder. In other words, r is the number that we get at the bottom of the long division process, and q is the number that gets constructed at the very top. And when we have this representation, we can take the three division problems that we did at the top of the board and rewrite them. I can write 79 as 6 times 13 plus 1, I can write 40 as 8 times 5 plus 1, and I can write 1234 as 13 times 49 plus 12. So using the terminology with the first example, 79 was the dividend, 16 was the divisor, the thing that it's dividing into the dividend, 13, the number that produced up top, is the quotient, and 1, the number that got produced at the bottom, is the remainder. It turns out that polynomials behave very similar to numbers in this respect. We can actually divide polynomials by each other, and let's formalize that in the following theorem. Let a and b be polynomial functions, where b is not identically equal to 0. We make that statement because I don't want to divide a polynomial by the number 0. It turns out that I'm allowed to divide a by b, and I get in return unique polynomials q of x and r of x that would be called the quotient and the remainder. And when I do this, I can express a as being equal to b times the quotient plus the remainder. And I'll even go a step beyond that. I can actually write a divided by b as q of x plus r of x divided by b of x. And like I said before, we're going to get very similar words and notions. So in this case, a of x is the dividend, b the divisor, q of x the quotient, and r of x the remainder. In terms of the remainder, we have two possibilities. Either the degree of the remainder is less than the degree of b of x, or r is just equal to 0 itself. In the latter case, we see that b would divide evenly into a of x. As a quick example, observe that x squared plus 4x plus 3 factors as x plus 3 times x plus 1 plus 0. We know that when I factor polynomials, I'm listing out all of the factors that divide evenly into the larger polynomial, so it makes sense that, written this way, I would have a remainder of 0. And one of the things that I can say is that the polynomials x plus 3 and x plus 1 divide evenly into the quadratic x squared plus 4x plus 3. But ultimately this shouldn't be too surprising. If I'm dividing a polynomial by one of its known factors, I should have a remainder of 0. But just like with numbers, what happens when I divide a polynomial by something that isn't a direct factor? We're going to see that in the next example. So can I divide x squared plus 4x plus 3 by x plus 2, something that isn't one of its factors? You can, and we can show how this works through long division. Right off the bat, we're going to look at x squared plus 4x plus 3 as the dividend, and x plus 2 as the divisor, and we're going to write it in the familiar format. I have my division bar with the divisor outside and the dividend inside. Similar to long division with numbers, I'm going to go through each one of the terms in my dividend and see if I can fit the factor x plus 2 into it. The way to figure this out is to do the following. We need to ask ourselves, what can I multiply the divisor x plus 2 by so that the term x squared appears? Again, this process might seem a little strange, so let's go over it again. We're trying to figure out what I can multiply the divisor of x plus 2 by so that x squared appears, because x squared is the first term in my dividend. If we think through some possibilities in our head, we'll find that multiplication by the factor of x will make x squared show up in the product. Here's what I mean. If I multiply x by x plus 2, I get x squared plus 2x. And this is what I want to happen. I want x squared to show up in this product. So what I'm going to do is I'm going to take that new character I came up with, x itself, and I'm going to put it at the top of my division bar, and this is going to be the first term in our quotient. And then I'm going to subtract the product, that product being x squared plus 2x. At the end of the day, this is very similar to long division with numbers. We're applying very similar concepts to polynomials, and with a little bit of practice, we'll warm up to it a little bit more. But what I've done is I have taken this new term x, I've multiplied it by my divisor, and this product that I get from that, which is x squared minus 2, I need to subtract from my dividend. Once I do that, I'm going to end up with 2x, and then I'm going to bring down that next term over, which is a 3. So the expression 2x plus 3 is what I now need. Now I'm going to ask myself, what can I multiply the divisor by so that a 2x shows up? Because the 2x is the first term in this new expression at the bottom of our long division. When we think about it long enough, if we multiply x plus 2 by the number 2, the number 2x will show up. This product is going to be 2x plus 4, so I'm going to subtract that, and this difference will give me a negative 1. Now at this point, I've gone through all the terms in my dividend. Just like with numeric long division, this would mean that I'm done. The expression that we constructed at the top is our quotient, and the expression at the bottom is our remainder. This means I can express the division of x squared plus 4x plus 3 divided by x plus 2 as the quotient x plus 2 plus the remainder 1 divided by the divisor x plus 2. It's purely circumstantial that the term x plus 2 shows up twice. It just so happens that x plus 2 is both our quotient and our divisor in this example. But this is how polynomial long division works. You go through each one of your terms in your dividend, and then you ask yourself, what can I multiply the quotient by such that that first term appears in the product? Not everything has to match, just that first term. When we started, I had to look at my divisor of x plus 2, and I had to multiply it by something such that x squared appeared, x squared being the first term in my dividend. And by thinking about it, it turns out that that value was x itself. And so I computed that product and subtracted, and then it just turns into a rinse and repeat procedure. Let's look at one last example. We're going to compute the polynomial division of 6x to the 5th minus 5x to the 4th plus 10x cubed minus 15x squared minus 19. Even though it's a bigger problem, fundamentally it's not different than what we just did, it just takes a few more steps. One thing I'll note is that underneath the division sign I have a 0x. Sometimes when I'm missing certain powers of x, it's good to put them in there as placeholders just to make the arithmetic a little bit more coherent. I have a divisor of 2x squared minus x plus 3, and the first term of my dividend is 6x to the 5th. So now I have to ask, what do I multiply the divisor by such that 6x to the 5th shows up in the product? Think about it this way. The divisor has a largest power term of 2x squared, and the quotient has the term that we're after, 6x to the 5th. So I can think about it like this. What do I multiply 2x squared by such that I see a 6x to the 5th? Well, I think I have to multiply by something with the number 3, because 2 times 3 gives me the 6. And if I want to increase that exponent of 2 to a 5, I have to multiply by an x to the 3rd. So this means that I'm going to multiply my divisor by 3x to the 3rd. And we can see that that product is going to give me 6x to the 5th minus 3x to the 4th plus 9x cubed. It doesn't matter that I have other terms showing up like that minus 3x to the 4th and plus 9x cubed. What matters is that I multiplied by 3x to the 3rd and it forced a 6x to the 5th to be present. So just like before, I'm going to take that new term, 3x cubed, and I'm going to write it above the division bar, and then I'm going to subtract this product. Once I do that, I'm going to end up with negative 2x to the 4th plus x cubed, and then I'm going to bring down that minus 15x squared. And right now it's just a process of rinse and repeat. My next term that I'm after is negative 2x to the 4th, and again I'm weighing this against the quotient of 2x squared minus x plus 3. All I care about is multiplying by something such that my 2x squared from the quotient increases to negative 2x to the 4th. If I want to turn a positive 2 into a negative 2, I multiply it by negative 1. And if I want to increase a power of 2 to a 4, I multiply by x squared. So I'm going to multiply my divisor by negative x squared to get a product of negative 2x to the 4th plus x cubed minus 3x squared. I'm going to write my values where they need to go, I'm going to compute my subtraction, and then I'm going to end up with a new term, or new expression, of negative 12x plus 0x minus 19. Alright, so after we're done subtracting, we see that the next term that we need is negative 12x squared. So if I look at my divisor, I'll see that I need to multiply it by a negative 6 to get negative 12x squared plus 6x minus 18. Now when I subtract everything, I'll end up with negative 6 minus 1. This has now constructed for me our final answer. I have a quotient of 3x cubed minus x squared minus 6 and a remainder of negative 6x minus 1. So I can write my entire fraction as the following. Alright, so that's pretty much it for polynomial long division. It does behave like long division with numbers, just with some added steps and slightly different ways of approaching this. But what I want you to do is go to the notes, because this does have some more examples with some annotations, including the examples that we're seeing in the video here. And please reach out if you need help.